Okay, hi guys. So in this lecture, we'll be discussing about the reaction of alkene with cold alkaline KMnO4. But before going into that, let us um, I have come up with a quiz so that you guys can answer, so that you guys have more clarity over what things are happening in with related to the stereoisomerism of compounds. Okay, so let's start off with that. So the quiz part is you just have to tell whether the statement is true or false. The first statement is all geometrical isomers are diastereomers. So this statement is true or false? All geometrical isomers are diastereomers. False. Okay. All diastereomers are geometrical isomers. This is again false. Okay. The fourth one is all chiral center containing compounds are chiral. False again. There can be meso compounds including the chiral center. A chiral center is must for a compound to be chiral. Chiral center is necessary for a compound to be chiral. Again, this is false. Why? We can have examples such as for being chiral, we can have alene, biphenyl, spiro, bicyclo. Okay, we have discussed all those stereochemistry of these compounds. Okay, so all chiral molecules are resolvable. So all chiral molecules are resolvable. So I hope you understand and remember the resolvability, that we can actually resolve enantiomers by passing on uh, optically active, purely optically active compound in the mixture, and then the diastereomers formed will actually separate the enantiomers. Okay, so all chiral compounds are resolvable. So for this, the answer should be false again, because you can have cases like amine inversion or flipping, right? So now we are done with the quiz part. Coincidentally, all the answers seem to be false here. Okay, so let's start with the reaction of alkene with cold alkaline KMnO4. Okay, so reaction of alkene with cold alkaline KMnO4. Okay, so in the example, let's suppose we have something like this, wherein we have a cyclohexene and we add a 1% alkaline cold dilute KMnO4 as a reagent. So this is called as Bayer's reagent. Okay, so the reaction would give something like OH on both the double bonds and both above the plane, plus MnO2 will drop down in the experiment as PPT. So let's talk about the colors of this. So this is colorless, this is purple in color, and this is actually brown in color. Okay, so this is also a test for unsaturation. How? This is also a test for unsaturation. Why? Because the colorless compound on reacting with the purple color compound forms a brown color PPT. This is brown color, not this one. So brown color PPT, hence it's a test for unsaturation. Okay, so how does the mechanism work in this type of reaction? So mechanism is something like, we have that cyclohexane ring and a double bond. So what happens when it reacts with MnO2? So KMnO4, sorry. So KMnO4 is basically something like this. KMnO4. Okay, so these the resonance takes place, and these two oxygen atoms actually combine with the carbon atoms there. So this forms a complex something like this, wherein we have oxygen here and double bond with oxygen here. So these two bonds break themselves to form O minus, so which will, the O minus will acquire H plus atom, and the MnO2, the brown colored PPT, will settle down at the bottom of the beaker. Okay, so this is the mechanism which takes place. So let's talk about the characteristics of the reaction. Characteristics of the reaction. Okay, so characteristic of reaction is simply the overall mechanism is a syn addition. So if you just look into this, both the OH will actually be either above the plane or below the plane. So this type of addition is called syn addition. So as we saw in case of H2PD, PT, PDNI. So in that case also, the addition of two hydrogens were either they were taking place above the plane or below the plane. So that was also an example of syn addition. Okay, so similarly we also have the concept of syn addition in reaction of alkene with cold alkaline KMnO4. Okay, so let us see another example, another characteristic. So let me first write down this is, so overall addition is a syn addition. Okay, and the second characteristic would be it is a test for unsaturation, as alkene and alkyne are unsaturated compounds. They will have a brown PPT of MnO2 settling itself in the beaker after we reacted with cold alkaline KMnO4. So second is it is a test for unsaturation. Okay, so let us now look at why actually cold KMnO4 is used for the reaction. So it is preferred over SO4, which also does the same thing, because obviously it is cheap and toxic. It is expensive and toxic. It is expensive and toxic. Okay, hence KMnO4 is preferred. Okay, so this completes our theoretical part. Now we'll come to the examples. So examples, so you have to identify the major product in case of you have been given this. So you have been cis 2 butene, so it is passed over with cold KMnO4. So what would be the output of this? The output for this would be simply 2OH would be on the same side, and CS3 would be something here. So this is a meso compound. Second example is cis 2 pentene rather, is passed over with cold KMnO4. So what would be the product formed out of it? So one product can be this CS3 here and obviously C2H5 here, and if they attack below the plane, then in that case 2OH will be here. So it is a formation of a racemic mixture or enantiomers. So it is enantiomers. We have third example wherein we have something like this, and this is passed on with alkaline KMnO4. Then it would have something like this. Okay, so only this compound would be formed, and this would be a meso compound. And as whether the OH groups attached below the plane or above the plane, we can actually rotate it across this perpendicular plane, and the same meso compound will be resulting. Okay, so what if we have something like, and we passed KMnO4. Now in this case, diastereomers would be formed. Diastereomer uh, will be formed. So whether diastereomer or enantiomers will be formed, not diastereomers. So we will have OH here. So it has two chiral centers but no plane of symmetry. So total number of enantiomers would be how many? If you just count them, it would be 2 to the power 2. So if we actually look into this carbon atom, it is having 1, 2, 3, and all 4 groups are different. So we can actually have this OH and this OH. Oh, just a thing. So let me draw all the structures first. So is this structure possible? No. Why? The OH will be attached to the, so ideally, as it has 2 chiral centers, so ideally total number of isomers should be 4, but let us verify whether they are coming or not. So this structure would not be possible, as one OH is below the plane and one OH is above the plane. But reaction of alkene with alkaline KMnO4 is a syn addition, so this type of product formation will not happen, right? Similarly, its mirror image would also not happen. Okay, so the only product is left is both the OH should be in the same plane. So one would be this, and another would be its mirror image. So total number are 2, not 4. Okay, let's look into some more examples of this. So we have fifth as trans 2-butene. So in trans 2-butene, if we react it with cold alkaline KMnO4 or Bayer's reagent, what would happen is, if you draw the structure of this, we will have a racemic mixture, OH here. It is the case when OH actually attacked below the plane, and this is the case when OH actually attacked above the plane. So it's a enantiomer. Okay, let's quickly look into some more examples. We have something like this. This and this. So here we have reacted with alkaline KMnO4. So the product formation would be something like either this or so does this compound have a plane of symmetry? Yes, it does have a plane of symmetry. So it's just a meso compound, or is it a meso compound? So if you look at it, the plane of symmetry, if we actually consider the plane of symmetry to be this as the plane of symmetry, then obviously yes, it is a plane of symmetry. And so if it's a plane of symmetry, then total number of a meso compound would be 1, because it is having two number of chiral centers, and according to the formula it would be 2 to the power n by 2 minus 1, so it would be only n is 2 here, so the total number of meso compounds would be 1 only in this case. But we are actually forgetting one more stereogenic area, which is the cyclohexane ring itself. Okay, so according to the cyclohexane ring, we would get, if the OH actually attacks below the plane, then we would be getting something like this. Okay, and if we actually get something like this, then if we actually flip it around, and we then would not be able to superimpose it on the first one, hence these two compounds are formed, and actually both are meso. Okay, let us look at the 7th example, wherein we have this, and we reacted with KMnO4. So what would be the products out of this? So let's say it is coming out of the plane. Okay, so it would be either this, or it can be this. By the way, these two are diastereomers. Okay, so in this case, if you calculate the total number of chiral centers, they are 2, but there are 3 actually stereogenic areas, so the total number of meso compound would be, as there are 3 stereogenic areas, so the condition that the compound is symmetrical but it has 3 stereogenic areas, so this formula would be applicable. So n is 3 here, the number of stereogenic areas, so 3 minus 1 by 2, which is 1. So this is the formula for calculating the meso compound. So in this case, 2 is the number of meso compounds. Okay, we can have OH, both OH attached lower on this CS3 again coming into the picture. Okay, so with this, let us take one more example in which I have this, again this, and I have this. So if you pass it KMnO4 over here, it would have something like this, OH and OH. Obviously you can draw the figures when they actually are above the plane and below the plane. So how many stereocentric, is it a meso compound? It is symmetrical, it is having 2 chiral centers, it is a meso compound. But if you look at it, the total number of stereogenic areas are 3, because 2 are the chiral centers and 1 is the ring itself. So 2 to the power 3 minus 1 by 2, so answer is 2. So two number of two products would be formed, and both would be diastereomeric. Okay, so with this we end this lecture. So in the next lecture we will be talking about classical and non-classical carbocations. So till then, good luck and goodbye.